So this is question number 42 and number 43 of the electric fields and the capacitors homework booklet. So in question number 42 we have a 1000 microfarad capacitor and also a 10 microfarad capacitor, and we charge both of these capacitors up so that they store exactly the same amount of energy. The potential difference across our 1000 microfarad capacitor is given in terms of V1, and the potential difference across our other capacitor, across the 10 microfarad capacitor, is V2. And we would like to know what the value of the ratio of V1 over V2 all squared is. So because we know that the question is asking us about capacitors in terms of energy, then we can simply write this equation down straight away. So we know that the energy stored in a capacitor is just a half times the capacitance multiplied by the potential difference squared. So if we put this into this particular equation for V1, the 1000 microfarad capacitor, we can also do the same thing for when we've got potential difference of V2 for the 10 microfarad capacitor, and we know that the energy in both capacitors is equal because it tells us in the question. So the energy is simply a half multiplied by 1000 times 10 to the minus 6 times V1 squared for this capacitor, and a half times 10 times 10 to the minus 6 times V2 for this capacitor, and we can put them equal to each other. We've then just got one equation. We just have to simplify it really. So if we multiply through by 2 and we divide by 10 to the minus 6, we basically get 1000 V1 squared equals 10 V2 squared. And then if we divide V1 squared by V2 squared on this side and divide by V2 squared on that side, in the end we end up with V1 over V2 squared is equal to 10 over 1000, which is 1 over 100. So therefore our answer is B. And then in question number 43 now, question 43 is a very bog standard question, and it's been asked a lot in past exam questions. However, there's a little trick to it, because what we've got is we've got a fully charged capacitor. We've got we have a 2 millifarad capacitor, and it's used as a backup for a memory unit, and it has a potential difference of 5 volts across it. Now this capacitor supplies a constant current of 1 microamp, and it's this constant current thing that's going to cause us that could potentially cause us some confusion. And what we want to know is how long this capacitor can be used for until the potential difference across it falls by 10%. Now, because this is a constant current, and the current coming from the capacitor needs to be constant, there's only one way we can do this. So if we've got a little circuit diagram like this, here's our capacitor, and the only way we can get a constant current is by attaching it to a variable resistor. So if we're discharging this capacitor, if we make the resistance high to start off with, it'll basically, if you like, reduce the current. And as the current is reduced, the potential difference across here is reduced, and so what will happen is the rate that the current flows out will start to reduce. If we then gradually turn down the resistance of this, then it'll stop the current less, and so therefore we can increase the current at the same rate that it's naturally decreasing, because current always decreases as it comes out of the capacitor. So by altering this, we can basically make the current constant. Now, the way that we approach all of these questions all of the time is like this. We know that the current is equal to the charge divided by time. So if we put an ammeter here, for example, that's basically what the current is. It's the charge per unit time. And we know for a capacitor, the charge stored on the plates is equal to the capacitance of the capacitor multiplied by the potential difference of it. And so therefore we can put these two equations together. So we get I, the current, is equal to the capacitance multiplied by the potential difference divided by the time. And if we rearrange this, then we end up with the potential difference equaling the current multiplied by the time over the capacitance. Now this is kind of important, because what this tells us is the capacitance is a constant, stays the same. In the question, we're told that the current is constant, so that I stays the same. So potential difference only depends upon time, and so the potential difference also goes down at a constant rate. So instead of having that typical graph of an exponential decrease in potential difference, in this case what happens is the potential difference goes down at a constant rate. Now this actually doesn't show that. What this shows is an increase in potential difference, because as time gets bigger, the potential difference gets bigger. What this equation is actually showing us is how much potential difference is being lost, if you like, by this capacitor. So therefore we have to change this equation very slightly. So the potential difference at any point is equal to our starting potential difference minus the potential difference that the capacitor is losing over time, and that's this equation here. So we can write this full equation out here, and this will tell us the potential difference at any point. Now what we want is we want to know how long, we want to know this t, basically how long this capacitor will discharge for until the potential difference has fallen by 10%. Well, we know that the starting potential difference is 5. 10% of that is 0.5. So this capacitor will basically make this memory unit work until the potential difference gets down to 4.5 volts. So that's our reduction in 10%. So that's our potential. That's our 10% reduction in potential difference. This is our starting potential difference. The current we know because it's 1 microamp there. The capacitance we know because it's this 2 millifarads here, and so we can basically put all the numbers into this equation and we end up with this. So we end up with T equals 0.5 multiplied by the capacitance over the current. When we put those numbers in, we end up with the time as being 1,000 seconds, and so therefore our answer is D. So that's quite an involved multi-choice question. A little bit later on we'll see that these come up again and again. There's at least another 2 examples in this booklet, but basically you use exactly the same method. You always start off by thinking about the current, and then you add in the capacitance and the potential difference from here, and then you think about what it is that you actually want to work out. So that's question number 42 and number 43 in the electric fields and the capacitors homework booklet.